All right, let's take a look at this review ticket, or not a review, but this application sheet together. I wanted you to do it on a video or give it to you in a video so that you can go as fast as you want, faster or slower. You have control of the speed and you can always pause, and if you don't get something that I said, you can back it up and watch it again. So let's do this together. What is the sum of the debts for the three most populous states? Express your answer in scientific notation. So the most populous states, here's the population. So here's the three most populous. So they want us to have the sum. So sum is the addition of those three. We're able to have a calculator. So we want to go get our calculator and just type those in. Now we may or may not need scientific notation. It just depends. So what do they want here? They want the debts. So they want these numbers. Okay, that might be too many zeros for this calculator to handle. I don't know. So let's go ahead and find out. 407 and then 3, 6, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it looks like it might have been able to do that. Plus 337 with 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Plus 276. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now look what the calculator did. It had to go to scientific notation in order to answer that. So we were able to put it in with all those zeros, but it's not going to be able to spit it out with all those zeros. So it's going to give it to us in scientific notation. That's 1.02 times 10 to the 12th. Well, that's what they wanted us to do anyway, express it in scientific notation. So we have that one already. It's 1.02 times 10 to the 12th power. Now, what that 12 means is we would move this decimal 12 times. If they wanted it in regular notation, in standard notation, we would move this 12 times. Well, look, 1, 2 gets it there, and then it would have 10 more zeros. So really what that number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. 1, 2, 3. So that's what it would have been had we not put it into standard notation. Okay, so that one, the calculator did that one for us pretty much. What is the sum of the debt of the least three populous states? So here's the least. See, they have the least amount of people. So now they want the sum of those three. Well, I think we can do this in our head because they all have 9 zeros. So it's 4 plus 4 is 8, 9, 10. That's going to be a 10 with 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. But now let's answer that in scientific notation. So right there is the decimal, and we want to move it back to there. So let's count that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 1.0 times 10 to the 10. Now that's a positive number because we have it's very large. So that's what those powers mean. If it's a large, giant number, which this one is, 10 billion, we have that power as a small. Okay, question 3. How much larger is the combined debt of the three most populous than that of the least three populous? Express in scientific notation. How much larger? What if it said how much larger is 10 from 6? We would do 10 minus 6 and that would give us our answer. So how much larger means they want us to take the big one and subtract the little one. Okay, well, we have a little bit of a problem here because they're not in the same power. So we got to get them to the same base. So this 102, I'm going to switch it over. I either need to switch this one to a 12 or this one to a 10. Doesn't really matter. A lot of kids were keeping the big one, so I think maybe I'll switch the little one and make this one go to a 12. So I have 1.0 times 10 to the 10, but I want that 10 to become a 12 on the number line. Okay, so I'm going to go that way. That means this decimal is coming that way 2 times. 1 puts it in the front, 2 puts it out there. So it's 0.01 times 10 to the 12. So there's the small one. Okay, so that's the small one. We want to know how much difference it is from that one. So here's the large one, 1.02 times 10 to the 12, and I want to subtract 0.01 times 10 to the 12. Okay, well, it's going to be times 10 to the 12. We didn't really even need to do that part because it's once you have the same base, you keep the same base. And now 1.02 minus 1 minus 0.01 is 1.01. So 1.01 times 10 to the 12. Okay, what is the sum of the population of the three most populous states? So now they want us to add the population of the three most populous. So 38 plus 19 plus 26. And then I don't need to type in all those zeros, I don't think. How about we just do 38 plus 19 plus 26. It gives us 83. So those add up to 83, and then I'll have 6 zeros after it. So 83 with 6 zeros. 83 million. Answer in scientific notation. Okay, so let's decimal, so I'll make it 8.3. Now let's see how many steps that was. It was 1, 2, 3, 4, 5, 6, 7. So 83 million, 6 zeros in this case, had a power of 7 because we had to go one more into that 3. What is the sum of the least populous states? And I want to add up these. I don't know, we could just type it in straight up, or I think I'll just add 3 zeros on the end of all of those. How about 690 plus 626 plus 576, 1892, and then add 3 zeros. So 1892,000. So there it is in raw numbers. And now let's turn that into scientific notation. So I'll move it from there to between the 1 and 8. 1, 2, 3, 4, 5, 6. That was 6 moves. Okay, approximately how many times greater are the population of the big states compared to the population of the little states? How many times greater? Times greater are the key words. What if I said, how many times greater is the number 14 than 2? How many times greater is this than 2? Well, that's not a point 14, that's a 14. How many times greater is 14 than 2? Well, it would be 7 times. This is 7 times bigger than this one. The way we can find out about it is take 14 and divide it by 2, and that tells us how many times greater it is. So when they're asking like how many times something is of something else, just divide the big one by the small one and we can see. So how many times greater are the big states than the little states? And we're talking about population. So we're talking about this one. How many times greater is this one than this one? Well, let's take a look then. The big one is 102 times 10 to the 12, and we want to see how many times 1.0 times 10 to the 10 will go in there. Now it does say approximately, so let's just take a look. Now remember what happens here. Now we have division. Division, we're going to take these and subtract. Division does one step lower, so the powers are going to subtract. So I know it's times 10 to the 2. And I'll use my calculator for the other part. Well, actually 1.02 divided by 1 isn't that big of a deal. Anything divided by 1 is 1, so it's going to be 1.02 times 10 to the 2. Actually, I think I just did the wrong numbers, didn't I? They want population, and it looks like I did debt. Okay, so let's get rid of those and actually do population. Here are the populations. We want the big population against the small population. Okay, so it's going to be the same idea. Let's just use the correct numbers. So 8.3 times 10 to the 7 is how many people are in the big states. 1.8 times 10 to the 6 are how many people are in the little states. Okay, same idea though. We're going to do division, so we'll do one step lower, which is subtraction. So 7 minus 6 gives us 10 to the 1. And now I'll use my calculator for that. 8.3 and 1.8. 8.3 divided by 1.8 is about 4.6. Did I type that in right? 8.3 divided by 1.8. Okay, I have about 4.6. Now it says how many times larger is that? 4.6, this is times 10, so that's the number 46 times larger. So the big states are 46 times larger than the smaller states. So to fit 46 of the small states, it takes 46 of the small ones to make the big ones. Okay, there will be some more like that. Let's take a look at question number 2. All planets revolve around the Sun in an elliptical orbit. Uranus's furthest distance from the Sun is approximately 3 times 10 to the 9, and its closest is 2.7 times 10 to the 9. Using this information, what is the average distance? Okay, average. Let's say you got a 6 on one assessment and a 7 on the other. How do you calculate an average? Well, you add them up and divide by how many there are. That would be 13 divided by 2, which is 6.5. That's how we do average. You add them up and divide by how many there are. So here we need to take the 3.004 times 10 to the 9 and add that with 2.749 times 10 to the 9, and then we'll divide that by 2. Okay, so let's do the addition, and then we'll divide the whole thing by 2. Well, nicely we have the same power, so we're not going to have to do anything with that. So we're going to have something times 10 to the 9. Okay, so we just need to add 3.004 and 2.749. Get my calculator. Might as well do it. Okay, 5.789 divided by 2. Now technically the 2 is times 10 to the 0 because 10 to the 0 is just the number 1. So 2 is just... So when I do the subtraction 9 minus 0, it's going to stay 10 to the 9. So really we're just going to be dividing this part by 2. So it's going to stay times 10 to the 9, and I need 5,789 divided by 2. So on my calculator I'm going to take that and divide by 2. And we have let's just round that. How about 2.89? Okay, and there we have it. I guess maybe we shouldn't have rounded it because the other problems had that many decimals in it also. So how about we go 2.8945? But that's okay. I'm going to leave that one the way it is. Okay, I was checking the answer and it wasn't quite right. Probably if I go back and watch the video, or you may have noticed, it doesn't look like I typed the numbers in quite right. It was 3.004 plus 2.749. That should have been 5.753 up here. 753. And then divide that one by 2. 2.8765. Okay, 2.8765 times 10 to the 9. It's almost the same thing. That was just a typing in the calculator error, so we don't lose too much credit for those. Okay, let's go to the next page. Here are the masses of the so-called inner planets. So what is the average mass? So there we go, average again. We'll add them all up and then divide by how many there are. So in this case, we'll divide by 4. So we got to add them all up. Okay, well, when we take a look at when we're going to add them all up, we have a small problem. Some of them are times 10 to the 23, and some of them are times 10 to the 24. We have to have the same power in order to, the same base in order to add them up. So I think I'm going to take the 23 and turn it into a 24. So on the number line, there would be 0. 23 would be out here. So I would go to the right one. So I'm going to take the 23 to the right, which means I'm going to take that decimal to the left. So mercury could turn into 0.33022 times 10 to the 24. So I took it 1 to the left. Then I would do the same thing over here to Mars. I make 23 go to 24. So that means the decimal has to go 1 that way. So that's really going to be 0.64185 times 10 to the 24. Now they're all times 10 to the 24s. So my answer is times 10 to the 24. So I just need to take this number plus this number plus this number plus this number. We'll take all 4 of those, add it up, and then it'll be times 10 to the 24. So let's get those in there and take a look. So let's see here. 0.33022 plus 4.8685 plus 5.9722 plus 0.64185. So it looks like we have 11.81277. Okay, so we have 11.81277 times 10 to the 24. Now we don't really have to fix it yet because we're not quite done. They want the average, so all that is we added them up. We still have to divide by 4. So again, it's kind of like we have 4 times 10 to the 0, so 24 minus 0 is still going to be a 24. So our answer here is still going to be times 10 to the 24, so I need this 11, whatever is divided by 4. So let's go ahead and take that and divide it by 4 from our machine. 2.953. You have to pick somewhere to round it, so I like to pick a few decimal places in there, so I think 2.953 seems like a good place. 95 would be okay too. So there we go. And now we don't have to fix that one. So see, that's why I didn't fix it here. I thought dividing by 4, 11 divided by 4, I knew would get down to just a single digit. So average, add them up, divide by how many there are. Number 4, the speed of light is 300 million meters per second. The sun is that many meters from Earth. How many seconds does it take for sunlight to reach the Earth? Well, if we have this big long distance and it's going this fast, if we take this big long distance divided by 300,000, that should give us the time. So let's see if we can't do that. So I want to do division. So I think I'll turn this one into scientific notation. 1, 2, 3, 4, 5, 6, 7, 8. So that would be, I want to divide it by 3 times 10 to the 8 power. So 11 minus 8, so my answer is going to be in times 10 to the 3. Remember, it's the top one divided by the bottom one. And now I'm going to use my machine to do 1.5 divided by 3. .5. Okay, they want to know, it doesn't necessarily say how do this in scientific notation, and that's going to be a number that they want to know how many seconds. So I do think I'll go ahead and move this. That's large, so that means move the decimal to the right. So if I go 1, that makes it 5, 2 makes it 50, 3 makes it 500. So it looks like our answer here is 500 seconds. Now, I told a story in class that I asked somebody how far away the sun was in light years or light time, and we said something about 8 minutes. Well, look, 500 seconds is 8 minutes, actually. If we do 500 seconds divided by 60, since there's 60 seconds in a minute, look, it's 8.3 minutes. So the sun is 8 minutes from Earth. 8 light minutes from Earth, or 500 light seconds. So there we go, 500. Okay, the mass of the moon is this large number. It would take approximately 26 million moons to equal the mass of the sun. Determine the mass of the sun. Okay, so if this is the moon and it takes 26 million of them, if we just multiply those together, we'll have the sun. So let's do some multiplication here. 1, 2, 3, 4, 5, 6, 7. That's the same thing as 2.7 or 2.6 times 10 to the 7. There's that one. And I want to multiply it by this one, 7.3 times 10 to the 22. So I'm taking how many moons times how much the moon is, and that should give me the sun. So multiply, PEMDAS. When it asks for multiply, what we do is add. So I'm going to take 22, add 10. So this is going to end up in terms of 10 to the 29 power. And now I'll use my machine to do 7 times 2. So I know I'm probably going to have to fix it because 7 times 2 is going to be somewhere around 14 or 15. So I'll fix it in just a moment. So 7.3 times 2.6, 18.98. Okay, 18.98. That would be good, but it's not between 1 and 10, so I need this decimal to go there, which means the 29 is going to go like that. So the 29 will grow to a 30. So we have 1.898 times 10 to the 30. Okay, the mass of the Earth is this number. The mass of Pluto is that number. See why we use scientific notation so we don't have to write all that or count all that? Compared to Pluto, how much greater is Earth's mass? Okay, how much greater? How much greater means they want us to subtract them to see how much bigger one of them is. Okay, so I'm going to take 5.9 times 10 to the 24. And so it's kind of like saying, let's say we have 10 and 7. How much greater? How much greater is 10 than 7? Well, it would be 3. So that's where subtraction comes from. We want to subtract these. So I'm going to take the Earth and subtract Pluto. Well, let's see. There's 3, 6, 9, 12, 15, 18, 19, 20, 21, 22. So that's 1.3 times 10 to the 22 that I want to subtract. Okay, in order to do addition and subtraction, we have to have the same power. So we need to make these the same. So that 22, I think I'll make it go this way so it's a 24. That way they're both the same. That means this decimal has to go this way 2 times. So 1, 2 makes it 0.013 times 10 to the 24. Now, we were doing the subtraction by hand when we did the homework assignment on this, but now we have our calculator, so we can just let the calculator do the subtraction. 5.9 minus 0.013, 5.887. So we end up with 5.887 times 10 to the 24. See, it's almost the same as what the Earth. It barely changed by subtracting out a Pluto, because Pluto is much smaller than the Earth. So what is the combined mass of the Moon, Earth, and Pluto? Okay, so there's the Moon, Earth, and Pluto. Here's Earth and Pluto, and there's the Moon. Okay, so we got the combined mass, so 7.3 times 10 to the 22, there's the moon. We want to add to that the Earth, 5.9 times 10 to the 24, and then we want to add to that Pluto. Now I think I'll just use this form of Pluto since I already have it in 24. So 0.013 times 10 to the 24, because we have to get them the same anyway. Well, since I already got that one to a 24 there, I'll just use Pluto like this. And now all we have to do is get this one to 24. So 22 goes that way twice. That means this decimal goes that way twice. Once, twice. So 0.073 times 10 to the 24. So that one plus that one plus that one. And we'll have our machine do just the rote addition. Okay, 0.073 plus 5.9 plus 0.013. 5.986. Times 10 to the 24 is all three of them together. And just as a notice, look, Earth was 5.9 of that. The Pluto and the Moon barely added anything because the Earth is so much bigger than the Pluto and Moon. Number 8, the Sun produces this many joules of energy per second. How much energy is produced in a year? And then it says, okay, a year is this many seconds. So it's this much per second, so we need to multiply it by that. So we have 3.8 times 10 to the 27, and we want to multiply it by this one. Okay, let's count. 1, 2, 3, 4, 5, 6, 7. That's 3.1 times 10 to the 7 seconds. Okay, when we want to multiply exponents, we add their power. So I know this is going to end up to be something times 10 to the 27 plus 7. So it's going to be 10 to the 34. And now I'll use my machine here. This might actually fit 3.8 times 3.1. 3 times 3 is 9, but probably not because that's almost 4. It's almost 4 times 3, so it's probably going to be too big. But let's look and see. So we have 3.8 times 3.1. Ah, just too big. 1178. All right, so we got to fix that. So we'll go one decimal that way. So it's 1.178, which means the 34 goes one spot that way. So 10 to the 35. On average, number 9, Mercury is about 57 million kilometers from the Sun, whereas Neptune is that many kilometers, 4.5 billion kilometers from the Sun. What is the difference between their distances? Difference means subtract. So let's go ahead and subtract them. So let's take the big one, 4.5 times 10 to the 9. And I want to subtract. Okay, let's count what this one is. 1, 2, 3, 4, 5, 6, 7. So that's 5.7 times 10 to the 7. In order to subtract, we have to have the same power. So I'll keep the 9 and move this one. So 7 can become a 9 with 2 steps on the number line. So I'll go 2 steps here. 1, 2. 1's in front of the 5 and then an extra. So 0.057 times 10 to the 9. So there's our subtraction. 4.5 minus 0.057, and I already know it's going to end in 10 to the 9. So 4.5 4.5 minus 0.057. 4.443. Okay, excellent. That's small enough that we don't have to fix it, so that one is done. Number 10, the mass of the Earth is approximately this much, and the mass of Venus is this much. Find their combined mass. Okay, they're already 10 to the 24 and 10 to the 24, so that's good. I don't have to fix this one. When I add these together, it's going to be 10 to the 24. 4.9 plus 5.9 is going to be too big, but that's okay. It's easy to fix. So 4.9 plus 5.9. 10.8. So that's too big, so I'll go ahead and fix it. So it's going to be 1.08. That means the 24 is going to go that way to become a 25. Okay, part B, given that the sun is approximately this big, how many times larger is the sun than the earth? How many times larger? So if we divide those two, we'll see the multiplier that makes how many times larger the sun is from the earth. So take the big one. So here's the sun, 1.9 times 10 to the 30. And if I divide the earth, which was 5.9 times 10 to the 24, I should get the multiplier to see how many times bigger the sun is. Okay, PEMDAS. When it's asking for division, what we do is subtraction. So 30 minus 24. So I know this is going to end in times 10 to the 6. 1.9 minus 5.9. Let's see what we have here. 1.9 minus 5.9. Negative 4. Wait, why did I say minus? Okay, we subtract the powers, we actually do the numbers. It's 1.9 divided by 5.9, sorry. 1.9 divided by 5.9 is 0.32. Maybe I'll go one more, 0.322. It was 0.322. Okay, that's too small, so I'll go one more to make it 3.22. And then if the decimal goes that way, the 6 goes this way on the number line to make it a 5. Now, I don't think I want this in scientific notation because sometimes that's a number that's hard to see. How many times bigger is the sun? So let's go ahead and crank this out to a real number, to the actual non-scientific notation, standard notation. This means move the decimal 5 times bigger. Okay, once, twice, 3, 4, 5. Fill those in with zeros and we have 322,000. It's 322,000 times bigger. 322,000 Earths would fit in the sun, is what that means. Okay, let's go on to number 11. The mass of a proton. So see, protons are really small, so that's a very small number. What is this in scientific notation? So since it's a really tiny number, it's going to be a negative powers. So let's get it counted. We want it to go right there. It's going to be 1.672622 times 10 to something. Okay, well, let's count them. Here it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. There it is as scientific notation. So that just gives a visual of what a negative 27 looks like. It's all those little zeros. Okay, the mass of an electron is this. What's that in scientific notation? Okay, so we got to get it right to there. So it's 9.109389291. That's where the decimal goes. So the first number is between 1 and 10. So let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 18, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So we'll make it times 10 to the negative 31. So you can see an electron is smaller by 4 decimal places than a proton. Okay, how many times heavier is the proton than the electron? Round your answer to the nearest ones place. Okay, how many times heavier? Times heavier. So we want to take the heavy one divided by the light one. So here's the bigger number. This is actually bigger because think about that negative 27 on a number line. Negative 27 is there, negative 31 is there. See, 27 is actually a bigger number. So this one is bigger. So let's take 1.672622 times 10 to the negative 27, divide it by 9.10938291 times 10 to the negative 31. Okay, PEMDAS. Ask for division, what we do is subtract. When we're talking ask for division, what we do is subtract for exponents. So I need negative 27, subtract negative 31. Negative 27, subtract negative 31. Okay, a negative and a negative make a positive, so it's really negative 27 plus 31. That should equal 4. Now, you shouldn't miss this at all, because even if you're bad, or you should check it at least, so we had negative 27 minus negative 31. Okay, here's the negative. So negative 27, here's the minus, negative 31. You can always check it and make sure that you did the subtraction right. So it's 4. Okay, so we know right now it's going to be times 10 to the 4 unless we have to fix it. So we probably are, because see how that's going to be 1 divided by 9. So 1.67222 divided by 9.1093891 is 0.1836. Okay, that's too small, so let's move that decimal 1 spot that way. So the 4 is going to go 1 spot that way. So we have 1.836 times 10. So a 4 going that direction on the number line makes it a 3. Now let's see what that number actually is. So let's go ahead and move the decimal 3 times so that it's bigger. 1, 2, 3. So that makes it 1,836 times larger. So a proton is almost 2,000 times larger than an electron. And we rounded it to the ones place right there. 1,836 times bigger. Okay, the U.S. national debt in 2019 is that number. The U.S. population is 329 million. What is each citizen's approximate share of the debt? Okay, so if I take this number and divide it by how many people there are, that's how much every single person owes. Okay, so 1.25, so I'm going to put the decimal right there. So let's count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's a very large number, times 10 to the 13. I'm going to divide that by 3.29. That's this one, putting the decimal right there. Let's count that one. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so division means subtract the power. So that's going to be 13 subtract 8. So I know it's going to be times 10 to the 5. Now I need 1.25 divided by 3.29. 1.25 divided by 3.29. 3799. 0.3799 times 10 to the 5. So I would need to fix that. So actually, let's go, we don't even need to fix it. Let's go ahead and just answer it now, because I'm going to go ahead and just make it bigger by 5. So 1, 2, 3, 4, one more 0. So 37990 each. $37,000 for every person in the U.S. is how much we all owe for the national debt in the U.S. So that's what every person owes, apparently. That's a lot. Okay, let's take a look at the next one. The area of California is 163,000 square miles, and the area of the U.S. is 3 million square miles. Let's round these figures to this. Okay, so that's to the 1, 2, 3, 4, 5. Yeah, see, they moved it back 5 times to 1.637, and 1, 2, 3, 4, 5, 6. So they moved that one, so it's times 10 to the 6. In terms of area, estimate how many Californias would fit in one U.S. And then, okay, so how many Californians will fit, one Californias will fit in the U.S.? Okay, so let's take the U.S. and divide it by California and see how many times it goes in there. 3.794 divided by 1.637. Let's take a look. How many Californias would fit in the U.S.? Okay, there's our, whatever it's going to be times 10 to the 6 minus 5, which is 1. Now I just need to do 3 divided by 1. It looks like it's going to be about 3. 3.794 divided by 1.637 is 2.3, about 2.3. Okay, so how many Californias so what number is that if we want to know how many Californias? This means make it one slide bigger. So one slide bigger is 23 times. It would take 23 Californias to make the United States. The average distance from Earth to the moon is this far, and the distance from the Earth to Mars is this far. Okay, so this is Earth, Moon, this is Earth, Mars. How much farther is Earth, Mars than Earth, Moon? So how much farther means subtract. So I'm going to take the big one, subtract the little one. So it looks like this one is the big one. So 9.24 times 10 to the 7. Subtract the smaller one, 384 times 10 to the 5. But in order to do subtraction, we have to have the same base. So I think I'll take this 5 and crank it up to a 7 by going twice that way. So we take the decimal and go twice that way. 1, 2, puts a 0 in front of it. 0384 times 10 to the 7. Now we can do subtraction. 9.24 minus 0384 times 10 to the 7. So let's get the machine for the rest of it. So I need 9.24, subtract 0.0384, 9.2016. Number 17, there are approximately this many grains of sand on Earth. That's a lot. There are approximately this many atoms in the human body. That's even more. Are there more grains of sand on Earth or atoms in the body? Look, this is a much bigger number, 27 moves versus 18 moves. There's many more atoms in the human body. There are more atoms in the human body than there are grains of sand on Earth. About how many times more atoms in the human body compared to Earth? So how many times more? So if we divide those together, we'll see how many times more there are. So let's go ahead and divide them. Let's take the big one divided by the little one. So the atoms, 7 times 10 to the 27, divided by the grains of sand, 7.5 times 10 to the 18. PEMDAS, divide, goes to subtract. So when they ask for divide, we will subtract. So 27 minus 18 is 9. So we already know it's going to be times 10 to the 9. And now I need 7 divided by 7.5. 0.93, it looks like. Okay, so, you know, when they say how many times, usually we don't want it in scientific notation, but this is going to be a really large number. Move the decimal 9 times, so once, twice to there, and now I need 7 more. So 93 with 7 zeros. 1, 2, 3, 4, 5, 6. So the human body has 930 million times more atoms than the Earth has sand. That's a lot. Okay, number 19. I wrote over that, I can't read it. Oh, in popular science writing, a common unit is the light year, or the distance that light travels in 1 year. Okay, so we're going to use a year to be 365.25 days. That's how come there's that 1/4 is how come there's a leap year every 4 years. And okay, 1 light year is this many kilometers. Well, here they have it in scientific notation, so it's easier to deal with in scientific notation. So 1 light year is this many kilometers. The distance to the nearest star, Proxima Centauri, is to the sun is approximately this many kilometers. How many light years away is that? So let's take the kilometers and divide it by the light years and see. So we have 4.013336473 and divide it by a light year. 9.46073 times 10 to the 12. How many light years away is the nearest star? Well, division means we're going to subtract the power, so it's 13 minus 12, so it's going to be times 10. And now I need all those other numbers in there, so let's type all that in. 4.013336473 divided by 9.46073 is 0.424. Okay, so let's not leave that scientific notation because they want to know how many light years that is. So that means move it 1 spot so it's bigger. So that's 4.24 light years. The nearest star is about 4 light years from the sun, from us. So the starlight that we see from that star happened 4 years ago. So that star might not even be there. Probably it is, but we're seeing it as it was 4 years ago. Okay, the Fornax dwarf galaxy is this many light years from Earth, while the Andromeda galaxy is this many light years from Earth. Which one is closer? See, this means move it 6 times that way. This means move it 5 times that way. This is a bigger number. So which one is closer? Closer to Earth is the Fornax. Is closer. Okay, 21. The average lifetime of the tau lepton is this very small number in seconds. Okay. I guess I don't need to zoom in. You have your own paper you can read. And the average lifetime, the neutropon, is this many seconds. Which subatomic particle has a longer lifetime? Okay, so this one moves the decimal back 17 times. So it's going to have 16 zeros in front of it. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 8, 4. So it went from the 8, 4 all the way back there. This one only moves it back 13 times. That's 0.00, so 12 zeros. 4, 5, 6, 7, 8, 9, 10, 11, 12, 2906. This one is much bigger number. It has much fewer decimals in it than this one is. So this one is larger. It's still really small, but it's larger than that one. So explain which subatomic particle has a longer lifetime. The longer lifetime is this one because the number is smaller. I mean, the number is larger. It's closer to 0 on the number line. So this is a bigger number, not closer to 0. It's closer to 1. This is a larger, it's kind of like this. Which number is larger? 0.1 or 0.01 or 0.001. See, the more zeros, the smaller you get. So the fewer zeros, the larger. That one's larger than this one. Okay, same thing. Which one of these is larger? Well, now they have the same amount of zeros. So it's going to be the bigger number. So this is 9.3000. This is 9.2879. See, the 9.3 thousand is a little bit bigger than this one. So which one is larger? That one is larger. 23. The mass of a neutron is approximately this. That's a small number. Recall that the mass of a proton is this, which is heavier. Okay, so which one of these is a bigger number? Okay, same thing. They both have the same amount of decimals, so we don't have to worry about that one. We only have to compare the actual digits. So we have 1.6749, etc. for this one. This one is 1.6726. Okay, see, it's tied right here. This one is bigger. The 4 is bigger than the 2, so that's when this one wins. So this one is heavier because it's a larger number with the same amount of decimals. The average lifetime of the Z boson is approximately this many seconds, very small. And the average lifetime of a neutral Rho meson is approximately this many seconds. Which one has a longer lifetime? So this one has 24 decimal moves, so it has 23 zeros in front of it. This one has 24 zeros in front of it. This one has more zeros. So it's point and then a whole bunch of zeros. This one down here is a point with fewer zeros. This one is bigger. The fewer zero is bigger. So this one is the longer, the bigger number. The fewer amount of decimal places is bigger. Approximately how much longer is the lifetime of Rho meson than Z boson? So how much longer? So they want us to subtract them. So we want the Rho, which is 4.5 times 10 to the negative 24. How much longer means we're going to subtract the other one. 3 times 10 to the negative 25. And we have to get these to be the same decimal, the same power before we can subtract them. So I think I'll just take this on the number line. We're going in the negatives now, so let's be careful. I want a negative 25 to become a negative 24. So I'm going to go that way to make it happen. So negative 25 goes that way to make it a 24. So that means this decimal has to go that way. So it becomes 0.3 times 10 to the negative 24. Now we can take this number and subtract it from this number. You can do it on your calculator, but 4.5 minus 0.3 is 4.2. So we have 4.2 times 10 to the negative 24 power. And we did the subtraction. Okay, there was using all of that stuff in context, in story problem kind of mode. So there'll be some problems like that on the major summative coming up.